we are looking at lesson 46, related rates problems. So kind of a big calculus problem, or a big calculus deal, so to speak. Goes along with some of these problems you see, like your number one problems in homework. Goes along with some of the setup for that, but going farther with them now and looking at related rates. So let's just jump right into example one, if we will. A 13-meter long ladder leans against a vertical wall. The base of the ladder is pulled away from the wall at a rate of 1 meter per second. Find the rate at which the top of the ladder is falling when the base of the ladder is 5 meters away from the wall. Okay. Guesses on the first thing I'm going to do here?
Draw a picture.
Yep. You know it. I'm going to draw a picture. The problem in general is the fact that I'm drawing a picture.
Especially with the picture, that would understand it, and one of his different, that would have no idea how.
Okay, well, I'm going to try and make it make sense. I think we should be okay here. So, okay.
Yesterday, my brain was so numb after I left that class.
Yeah, I couldn't do anything involving that.
Okay. There's my wall. Nothing fancy here. Here's my ladder. And let's see, what do we know about this ladder? This ladder is 13 meters long. Okay. It's a vertical wall, which means that wall makes a 90-degree angle with the ground. Smart moves here. Now, what does it specifically talk about? The base of the ladder is pulled away from the wall at a rate of 1 meter per second. So that means the base of this ladder right here is going to be moving away from the wall. Or in other words, the length of that side of the shape is changing at 1 meter per second. We'll talk about what that actually is here in a moment. And then, let's see. Away from the wall at a rate of 1 meter per second. And then they ask us to find the rate at which the top of the ladder is falling. So we're trying to find the rate at which this side is changing because that top of the ladder is falling. When is it? When the base of the ladder is 5 meters away from the wall. Okay, so first of all, we know the ladder is 13 meters. How about some variables for the other two sides so we have something to refer to them as? I'm going to go with X and Y. I'm not trying to do anything tricky here, I promise. X and Y, nothing fancy. If you guys want something fancier, well, more power to you, but there you go, see? Logan could go fancy. I'm going to stick where I'm at. Now, when we talk about these related rates, okay, the rate of change, what do we know about rate? Rate is another word for what? Yes, but not where I'm going with this. I mean, I guess, huh? I mean, yes, but we're not going to talk about velocity in this problem. But, okay, let me take it this direction. Velocity in calculus is equivalent to what? The derivative, yes? Okay, so we're talking derivatives is all that I'm trying to get you guys to. Okay, so you guys came up with velocity. My brain was trying to get you to think slope. But you know what? I'll take the physics version instead. We'll go with it. Okay, I got it. I can make it work here. I'll adapt. Okay, so whether I think slope, you guys think velocity, it's all rate, and it all means the derivative in terms of AP calculus. Okay? That's what I need you guys thinking here. So when we talk about this rate right here, is this side of the, what shape is this? A triangle, right? This side of the triangle is changing at a rate of 1 meter per second. Well, this is the change of side x, right? And it's going to be the change of side x in relation to time. And so that 1 meter per second is what I'm going to call dx dt. And I didn't write that in very well, sorry. That says dx dt there is that 1 meter per second because the rate of change is changing at 1 meter per second. So the side length of x is changing 1 meter per time unit. Okay? Now, we're being asked to find here the change of the vertical side, which means we're being asked to find the change of side y. So we're being asked to find dy dt. That's our goal of this problem, to find dy dt. And we specifically want to find the rate at which the top of the ladder is falling when the base of the ladder is 5 meters away from the wall. So that means when what is 5? When x is 5. Now notice, I am not going to change that side length to 5 because that's only at the time we're finding it. Is x always 5? No. X is changing. So the ladder is always 13, but x is not always 5. Okay. I need an equation to set this problem up. Okay, I drew a picture. I labeled everything I could. I came up with, okay, I know what I need to look for. I need to look for dy dt. What's an equation that connects this shape together? Pythagorean theorem? Yep. What's the Pythagorean theorem read for this particular triangle? Okay. X squared plus y squared equals 13 squared. Okay. Now, based on the fact that we're given dx dt, we have to find dy dt, we're going to take the derivative. We're going to differentiate this equation. Now, keep in mind, this whole problem is in respect to time. So every time we take a derivative, we're going to put the dx dt, dy dt, whatever it is with it. Okay, whichever differential we need with it. So, derivative of x squared. 2x, and then we're going to say dx dt. Plus, derivative of y squared. 2y dy dt. Derivative of 13 squared. 0, because 13 squared is just a number, and the derivative of a number is 0. Now, we have a couple of different ways you can do this. Some people will teach to go ahead and start plugging in all the values you know, and then solve for dy dt. Other people will say, okay, let's go ahead and solve for dy dt, and then we'll plug everything in at the end. Honestly, it kind of depends on the problem, but I'm going to say, since we're searching for dy dt, let's go ahead and solve this equation for dy dt, which means I'm going to keep the dy dt term on the left. How do I move my other term? We're going to subtract the 2x dx dt over. So I have 2y dy dt equals, and when I subtract the 2x term over, it's going to be negative 2x dx dt. How do I get dy dt by itself? Divide by 2y. So if I divide by 2y, then dy dt becomes, what happens when you do negative 2x divided by 2y? Negative x over y, the 2's can cancel. So I'm going to say negative x over y dx dt. And then officially, with a little bit of work, we can fill in everything here because we will know everything. So, dy dt equals negative x over y. Negative, what's x? 5. Because now that we're at the end and we're trying to find dy dt, we're trying to find dy dt when x equals 5. So negative of, I really just wrote x. Okay, so negative of 5 over y, we'll come back and talk about y in a moment, times dx dt. Do we know dx dt? 1 meter per second. Yes, that was the change in the base side. So times 1. I need a value to plug in for y. Where do I get the value to plug in for y? Pythagorean theorem. Because we want to know what y is when x is 5. So the idea of go back and use x squared plus y squared equals 13 squared. And we're going to use when x is 5. So 5 squared plus y squared equals 13 squared. 13 squared is 169 minus 5 squared, so minus 25. 169 minus 25, 144. And the square root of 144 is 12. So what are we going to put in for y? 12. Oops. So I have negative 5/12 times 1, which is negative 5/12. Negative 5/12 what? Meters per second, because it's a change in y in relation to time. Why is it negative? Because it's going down, right? Okay, that ladder is moving down the wall and that length there is shorter than. There are connections between calculus and physics, so.
At least this is
Calculus based on physics.
Okay.
I think that'd be easier if our ratio was
We'll take the calculus based physics.
Okay, questions on this one?
And by the time you calculate base physics, you already been to algebra-based physics. If you go back for a second round, that's your own fault.
Yeah, that's true.
Okay, let's try example 2.
Taking calculus at the same time.
A 6-foot tall man is walking straight away from a 15-foot high street light. At what rate is his shadow lengthening when he is 20 feet away from the street light if he is walking away from the light at a rate of 4 feet per second? And what am I going to do with all those words? Draw a picture. What?
Assume it's daytime and the street light isn't on.
Well, or is it nighttime and we're talking about the shadow from the street light?
I think that's what the problem is.
So,
You could say it's not
If it's
everything.
daytime, it's shadow. Well,
Well, we would have a shadow, but
it's a shadow from the light, okay?
changing very slow.
Okay. Now, can you guys visualize what picture I'm drawing here?
another triangle.
Triangle?
We've got triangles, right?
Triangle in there.
Huh?
There's probably a triangle in there. Triangle.
Triangle. Okay, so we've got a street light here. This is our, and I'm not getting fancy. Okay, you get fancy. So there's my street light. And what do we have walking away is
A 6-foot tall man.
6-foot tall man. So there we go. there we go. I got my light here over at the left. I've got my 6 foot tall man. He's walking away. Typical problem here. Let's see. He is 6 foot, so I'm going to label him. How tall was the light? So 6 foot tall man is walking straight away from a 15 foot high street light. At what rate is his shadow lengthening when he is 20 feet away from the street light? If he is walking away from the light at a rate of 4 feet per second. Okay, so we need some labels here. What? He's moving at 4 feet per second. So before we talk about the fact that he's moving at 4 feet per second, I'm going to label these. And I probably use labels I got from the book, I'll be honest, because I have X and L here. Where is his shadow?
It's on the right side of it.
His shadow is right here. And so that's what I called L, because length of the shadow, and as I said, it's probably what the book used. Okay, use whatever variable you want. And then we also need a variable for the distance between him and the light. And so I just have X there. Now, okay, let's go back one more time. 6 foot tall man walking straight away from a 15 foot high street light. At what rate is his shadow lengthening? At what rate is his shadow lengthening? What is that I'm trying to find? It's the derivative of L. So yes, dl dt. So what we're trying to find is dl dt when he is 20 feet away from the street light. So we're trying to find dl dt when what is 20? When x is 20. Because we want to know when he's 20 feet away from the street light. Now, notice, am I putting that 20 into the figure? No. We do that at the end. We don't put it in right now. Okay? When they give you that, when something is a certain number, don't put it in till the end. So that will be when x is 12 later on. If he is walking away from the light at a rate of 4 feet per second. What is that 4 feet per second? What is changing at 4 feet per second? He's walking away from the street light, so x is changing at 4 feet per second. So in other words, that 4 feet per second is dx dt. It was feet per second, right? Yeah. Okay, do I have all the information down? I think I do. Okay, we have our picture, we labeled all the information we can, I wrote everything down that I can. I need an equation to connect all this. When you've got the light pole and the guy, and we're talking about the shadow on the ground and stuff, what have I created? Two similar triangles. Okay, so this is not Pythagorean theorem, this is similar triangles. And we can set up a proportion then. So, we've got to set up a proportion. We can do, and I don't know how you guys do your proportions, we can do side over side equals bottom over bottom, or we can do side over bottom and side over bottom. Am I making sense, or is that... You do the side over the bottom. So I was going to do side over side is what I was going to do, but I don't know that it it doesn't officially matter in that it will all work out the same. So if you do, is that what a lot of you guys do?
Yeah.
Side over the bottom? Okay. So let's go for the small triangle. My small triangle being right here. Yes? Are we okay with that? So his height of 6 is proportional to what? The length of his shadow, L. So I'm going to say 6 over L is equal to, so we did his height to his shadow is proportional to the height of light, 15, over its distance across the bottom, which is x plus L. So 15 over x plus L. How would be a good way to get the equation to work with here? Cross products, cross multiply. I agree. And remember, if you set it up differently than mine, like if I look at my notes right now, I did 15 over 6 and x plus L over L. I know mine is equivalent because my cross products are equivalent. Okay? So, cross products of, let's see, 15 times L is 15L. 6 times x plus L is going to be 6x plus 6L, if you will. At some point, we need to take the derivative. We could go ahead and differentiate right now. Or, you want to clean it up a little bit? I personally would clean it up before I differentiate, meaning, what do you guys notice?
We can subtract 6L from both sides.
Yep, I would subtract the 6L from both sides, and then that will give us 9L equals 6x. Technically, if you want, you could divide both sides by 3 if you want smaller numbers to work with. In other words, I could leave it as 9L equals 6x and proceed, or I could divide both sides by 3 and say that this is 3L equals 2x. I mean, at some point it will reduce. We can do it now or later. Okay. Differentiate. And I should have used the word earlier. This is our implicit differentiation, right? Where we're taking the derivative and with respect to, in this case, well, are we doing t here? So what's the derivative of 3L? 3. And then what? dl dt. Derivative of 2x? 2 dx dt. Okay, what do we need to solve for? dl dt. So if we're solving for dl dt, divide by 3. 2 divided by 3 makes it 2/3 dx dt. And officially, we're trying to find this when x equals 20, but my x dropped out, so I don't even have the 20 to plug in. What is dx dt, though? 4. So dl dt is 2/3 times 4, which is 8/3 what? Feet per second.
Doing this very hard. I think that I messed up because all the variables dropped out. Didn't even matter.
The 20 did not matter, exactly. It does occasionally happen. The 20 doesn't appear like it's going to be extra information, but it is. Okay, moving along. Example 3. A conical container. Is that how you say that word? Conical? Because conical doesn't sound right, and that's the only thing I can come up with. So I think it's conical. I just was second guessing myself. A conical container has a height of 9 centimeters and a diameter of 6 centimeters. It is leaking water at the rate of 1 cubic centimeter per minute. Sorry. Find the rate at which the water level H is changing when H equals 3 centimeters. I'm sorry, just your random comment back there just made me laugh. I'm trying to read this in all seriousness, but okay. Now that we've got that out of the way. It sucks since leaking water. Okay. Okay. So, conical container, in other words, a cone. If it's holding water, we're going to draw an upside down cone, so an ice cream cone, so to speak.
It's like one of those things where they have the paper cups that
Yeah.
There you go. It's a
I wouldn't want my conical container leaking water.
Okay, so conical container has a height of 9 centimeters, which keep in mind, when we talk height, that is going to be your distance straight up the middle, right? And it has a diameter of 6 centimeters. It is leaking water at a rate of 1 cubic centimeter per minute. Leaking water at a rate of 1 cubic centimeter per minute. What is that? No, but I mean, like, what is that in terms of this problem? What is it if we're leaking water at this rate of 1 cubic centimeter per minute? What is that that's changing? The volume. So that leaking water at 1 cubic centimeter per minute, first of all, cubic centimeter gives you a hint, but that is volume, and so this is dV dt. So what is dV dt? No. It's leaking water at a rate of 1 cubic centimeter per minute. So since it's leaking water, it's negative 1 cubic centimeter per minute. So that's dV dt. That's given is what I'm trying to get you guys to understand here. Because that's the changing of the volume. Now, what are we being asked to find? Find the rate at which the water level H is changing when H equals 3. So what is it I'm trying to find? dH dt. Good. So we're going to try and find dH dt when H equals 3. And what you have to consider here is that there is some water level inside this cone, right? We don't know where, but there's some water level inside this cone. And that water level is constantly changing, right? It's going down in this case. And we are specifically going to be asking about when H equals 3. So what I need to get you guys to connect here is that the normal height, when it's all the way full, is 9, yes? We're going to be looking for this height right here. How do I want to do this? I guess what I'm trying to get you guys, can you guys see if I show you two similar triangles here? We have the big triangle here on the right that uses the whole height of 9 and the given diameter. But then we're also going to have a triangle down here. And that's what we're going to have to use to be able to connect some values. Okay, and maybe I should have saved this for later, but I jumped right in, sorry. So if we think about a triangle within a triangle, and this is coming from here, right? What is the height of the big triangle here? 9. And what is this across the top of the big triangle? 3 because it's the radius. Good. And then what we don't know is we don't know what level this is at right here. Okay, so I'm just going to use R for this radius here that we don't know. And I'm going to use H for this height right here that we don't know. Okay? And the whole point is, set up a proportion with me. Trying to think, which way are you guys going to do this? You're going to stay within a triangle, aren't you? So if we set up proportions here, you would say what? Okay. 3 over 9 equals R over H. Because 3 from the big is the radius, 9 is the height, and then radius over height. Okay. I am a step ahead of myself, I just realized. Okay, this shows us the connection between R and H. And I just realized I am a connection because you don't know which one you need to solve for yet. So we'll come back to that here in a moment because we're going to come back and use that. What's the overall formula that ties this all together? I should have done that first, sorry. We're talking about what? The cone, how much water it holds, it's leaking water. So we're talking about dV/dt, so we need the what formula? Volume. Now, okay, how good are we? Do we remember volume of a cone formula? It does have a 1/3 because it's 1/3 of what a cylinder would be. Pi r squared h, yep. Okay, so volume of a cone. If we go back to volume of a cylinder, that's pi r squared h. And then a cone is 1/3 of that. So 1/3 pi r squared h. Now, here's where you'll see, when we go to take the derivative, this is in terms of R and H. Using a product rule would get really messy right here. So, we have this right here that connects R and H together. We want to make this equation to either all be in terms of R or all be in terms of H. What is it we're looking for later? And what is it that we know later? Later we'll know H is 3 and we'll be looking for dH dt, right? So we want this formula to all be in terms of H. We want to forget the R. So we're going to take this down here and solve an equation for R that will then be in terms of H. Am I making sense? Again, I messed up the order of this problem. Okay. I don't know if that reassures me or not. Okay. Okay, give me an equation here. Cross products. What do cross products say? Okay, either 9R equals 3H or 3H equals 9R. If I want to replace my R and get rid of my R, I need this solved for R. I need it to be R equals, because then I'm going to replace my R with H's. So if I solve this for R, what's 3H divided by 9? 1/3 H, or H over 3. So now what I can do with this, and again, as I said, I kind of goofed up my order here, is I can go and replace that for R. So V equals 1/3 pi. What am I inputting in place of R? H over 3, quantity squared, times H. Clean this up. First of all, it's going to be H to what power when I put that all together? 3rd, because there's H squared here times H here. And let's put all of our coefficients out front. We already have a 1/3 out here. What's in the denominator here? 3 squared, which is going to be 9. What can I multiply this 9 over into? The 1/3. 1/27 pi h cubed. Or actually what I'll do is I'll put the pi over the 27. Okay. Sorry. Are you with me here? We have the 1/3. The 3 squared makes it over 27. You can say 1/27 pi h cubed, or you can say pi over 27 h cubed. Moment of processing. Well, I'm not ready to plug anything in yet. Don't plug anything in until you take the derivative. We have to take the derivative first. So what's the derivative of v? dv dt, good. Pi over 27 is just constants, right? What's the derivative of h to the third? 3h squared. Now if you take that 3 and you multiply it by the pi over 27, 3 pi over 27, or in other words, pi over 9. So pi over 9, h squared, dh dt. Now you have options. You can either solve for dh dt, or on this one, what I honestly often do is I just go ahead and plug in right here. Just kind of showing that, it depends on the problem. This one, I don't know. I don't think it would be bad either way. Does that make sense? So if we go ahead and plug in, we should know everything, I hope. What do we know for what do we know dv dt is? -1. That was a change in volume. Equals pi over 9. What's h at this point? 3. So 3 squared times the dh dt we're trying to find. Now, pi over 9 times 3 squared is what? Pi. So I have -1 equals pi times dh dt. To solve for dh dt, divide by pi. And so what is dh dt? -1 divided by pi. And what would be my label here? Not cubic centimeters per minute. No. Okay, so, but use the idea, the cubic centimeters per minute was the change in the volume, yes? And so volume is a cubic unit. And so it was dv dt, so cubic centimeters divided by minute. Now it's dh dt. What would the height be measured in? It would just be measured in centimeters. So this is going to be centimeters per minute. You were almost there. You really were. And again, it's knowing that, okay, we were given cubic centimeters per minute, but that was for volume. We need height, so just forget the cube. Now, if it was the change in area, then we would have been talking centimeters squared per minute. Okay, We've got one more. Can we get it in? Sorry, we got a slow start. That was my fault today. And then these just take a little bit to go through. Okay, let's try it. Air is pumped into a spherical hot air balloon at a rate of 25 cubic feet per minute. Find the rate of change of the surface area of the sphere when the radius is 5 feet. I don't draw a very good sphere. A sphere being a 3D circle, right? So, sorry, you just get a circle from me. I'll label it a sphere, but that's what you can draw your own sphere. More power to you.
I don't know how. Just give a circle and then put the dotted oval
Okay,
like that.
I'm just drawing my radius in. Okay, let's get going here. Air is pumped into a spherical hot air balloon at a rate of 25 cubic feet per minute. What is that 25 cubic feet per minute? dV/dt. We know it's dV/dt because it's 25 cubic feet per minute. Anytime I see cubic, I'm thinking volume. Find the rate of change of the surface area. So that means I'm trying to find what? I was going to go dA/dt, just because A is generally area. So we're trying to find dA/dt, the change in the area, when radius equals 5 feet. Okay. I will need some formulas.
Sphere is 4/3 r
I don't know, are you trying to do area or are you trying to do volume?
squared.
So volume is 4/3 pi r cubed. And actually, we're going to need both here. And surface area of a sphere is 4 pi r squared. Yep. I was debating which I wanted to write down first. I don't know that it matters, but. Okay. Area is 4 pi r squared. And the key is when you hear area, know it's a squared, right? When it's volume, it's the cubed. So volume is 4/3 pi r cubed. Now, we're going to have to use a combination of those two formulas because they're giving me dV/dt, but they're asking me dA/dt. Let's go ahead and take the derivatives of both of them. They're both only in terms of r, so that works. The derivative of, let's work with the area just because it's what I wrote down. Derivative of A is well, for just the A part, dA/dt. And then, yes, derivative of 4 pi r squared is 8 pi r, and then what do you tack on at the end? dr dt. Okay. Let's go ahead and do the same thing with the volume formula. What? You do. Sorry, it was taking me a moment to figure out what you were talking about. So derivative of v is dV/dt. Derivative of 4/3 pi r cubed. 4 pi r squared, and don't forget dr dt. Okay, so ultimately, we're being asked to find what? dA/dt when r is 5. So we can plug in a 5 there, yes. But what do we not know? We don't know anything about dr dt. That's our problem right now. But guess what? We have this other formula. In this other formula, dv dt, which we know dv dt, yes. R, we know R at the time. And then what would that allow us to find? dr dt. Do you see where I'm going with this? Okay, so I'm going to go ahead and fill it in right there. dv dt is 25, 4 pi, what R am I using? 5 squared times dr dt. Let's see, 4 times 5 squared, 4 times 25, so 100 pi dr dt. If 25 equals 100 pi dr dt, what do we get when we solve for dr dt? 25 divided by 100 pi, which is 1 over 4 pi, if you will. And what's that allow me to do? That tells me dr dt can be used as 1 over 4 pi, and I can plug it in. So, dA dt is 8 pi, what am I using for R again? 5 times dr dt, which is 1 over 4 pi. Clean it up and you're there. 8 times 5 is 40. 40 divided by 4 is 10. Pi over pi will cancel, and so I have 10. 10 what? If this is dA dt I'm finding. Feet squared per minute. Made it, barely. Okay.